So welcome to the seminar of the Astani Department of Civil and Environmental Engineering. I think we are getting close to the end of the semester, so I think I must congratulate you for being here. I know that all the pressure that you are experiencing now at this, as the semester is about to finish and we have all these finals and exams. Now, our speakers today is Salvatore Caronna. Salvatore is a leading expert in the field of geotechnical data management and reporting. Salvatore serves on several geotechnical data interchange committees, including DIGS, which stands for Data Interchange for Geotechnical and Geoenvironmental Specialists, Cosmos, PEER, Cosmos, and as you know, Cosmos has to do with the strong motions. It's an institution which collects all the strong motions in the nations and possibly in the world. He's also serving on the Computational Geomechanics Subcommittee of ASCE, Geotechnical Institute, and he's also a contributor to the UK-based AGS data interchange format. Salvatore is the author of numerous papers on geotechnical data management. Salvatore is also the president and founder of GINT Software, which is one of the oldest software company on borehole for borehole logs, and I think I've been using this software for many years. So his company, GINT, provides geoenvironmental and geotechnical software for data management and reporting, and it's used by transportation authority, government agency, consulting firm, and educational institution worldwide. Now, Salvatore is not going to give us a pitch today for his software. I kind of told him not to do so. He's going to talk about general ideas. Okay, he's going to talk about geotechnical and geoenvironmental data management. Salvatore, welcome.
Thank you, Professor. Oh, for an introduction. Yes, today I'm going to be discussing a submarine. Yes.
We have to wire you.
Yes, go ahead.
Stop that inside.
Mm-hmm. Particle. Yeah. There we go. Is that all right? Yes. Before I start, I'd like to ask the students here, have you had any classes whatsoever on data management? No? Didn't think so. I've given this talk in a number of universities, and that's the same answer I get everywhere. And to be fair, you've got a very short time to learn a lot of things. And database management is not considered something you really need to know. But in the real world, it becomes a really big issue. The talk I'm going to be giving to you today is a condensed version of a short course that myself and Dr. Scott Deaton of Data Forensics put together for GeoCongress 2005, 2006. And we're going to be giving the same class next year in GeoFlorida 2010. All right, let's move on. Why is data necessary? Well, okay. In the end, all the computer work you do, all the stuff you would do with our software or any other software, has to end up helping you make a better decision. That's what it's all about. And you can't design strictly from software. The software is a tool. It is not the goal. And one of the things that you really need to be able to do with your data, and there can be lots of it. You've got downhole information, you've got field data, laboratory data, you may have cross-hole data with seismic surveys. You could have all kinds of different kinds of information. You need to be able to view that data, create data views, lots of different kinds of data view. A borehole log is a data view. An Excel graph of SPT versus depth is a data view. But it'd be more powerful, you could put the borehole log with the plot of SPT versus depth. That's a very simplistic example, but that's the concept. You want your data to contain, your database to contain all the relevant information, and you want to be able to view that data in different ways, to be able to correlate, to be able to try to understand patterns that are happening underground. Today, generally data management is an ad hoc process. Very typically, people go out in the field, log their holes, write it down on a piece of paper, bring it in. Sometimes it'll go to the CAD person who will then draft up a log. It'll go to someone else to put it into Excel to do some plots. It'll go to someone else to plot sections, et cetera, et cetera, et cetera. You're touching the data over and over and over again. Every time you touch the data, every time you copy it manually or do some manipulation on it, is one more opportunity to make a mistake. It has to be QA'd and QC'd. If you find the original data is wrong, you now have to go and track down all the reports that were generated by that data. It's a very, very labor-intensive operation. It's a very error-prone process, and it happens every day. A quick anecdote, a big client of ours, will not be mentioned, you know them, very typically what happens there on their geotechnical labs, every lab test, be it a triaxial test or a water content, gets its own Excel spreadsheet. It's fine, it works. And then when they want to put that data onto their log, they retype it into our software, the parts they need. Then, at the end of the job, they want to summarize all their lab tests. Literally, an engineer sits down and opens up every spreadsheet and retypes the data in a tabular form in Excel. It can take 1 to 2 days. This is not the way we should be working in the 2000s. But that is not unusual. Also, many times inappropriate tools are used to manage the data. And unfortunately, Excel is a huge boon to the engineering community, and it is a huge bane to the engineering community because it's used inappropriately. It's like discovering a screwdriver and you're using it for everything, including pounding in nails. It's inappropriate to use a screwdriver to pound in nails. It's inappropriate to use Excel to do database management. It's fantastic at certain things. You wouldn't use a hammer to screw in no, you do that too, but it's inappropriate. You want to use the best tools for the job. And many times when you are using appropriate tools, proper relational database management tools, many times the implementation is not good. We'll talk about that as well. So what we're going to talk about, what is database management? Why is it important? How does it benefit me? And some basic database concepts. So basically, it allows you to use your data efficiently and effectively. This is very, very important, the effectiveness of that. Many times I've heard of people that they have different departments. He handles the water levels. He handles the slope inclinometer data. This person analyzes the downhole geophysics, et cetera, and they never talk to each other. If it's all in one database, you can actually start correlating those things together. Then you're really using your data effectively. So data management systems manage the attributes and metadata. Metadata are data about data. You pick up a report that's 10 years old, and you want the blow count information from that report, and there it is. You've got N values. Well, what size hammer did they use? What was the drop? What was the size of the sampler? All those things impact what those N values mean. And that's the metadata. So it's very important, and that's something that's not done a lot. Not enough, anyway. All right. So this is a typical flow of data in a usual company. They'll get the manual data collection. They'll create the log. It goes through a QA/QC process. You produce your boring log. Then they'll take, again, the field data and put it into CAD, go through a separate QA/QC process, produce other reports, et cetera, et cetera, et cetera. This is typically the way things are done. This is the way it really needs to be done. Hopefully you're collecting your data digitally. And you QA/QC it. and then you run it through report generators to get everything. So you're all working with one source of data. It's been QA, QC once. And then you produce your reports, your data views from the same data. And if down the road you find there's a mistake in the data, you change it in one place and regenerate your information instead of redrafting. Yes? Yeah.
What is QA?
Oh, I'm sorry. Quality assurance, quality control. Yeah, why is it important? For one thing, to be more efficient. I mean, it is very expensive going through the processes I just described. We just can't afford that expense anymore. That's one of the many reasons. I've already talked about those. Okay, what are our design objectives? We want to produce useful, accurate, maintainable, and reusable information. So we need to store our data in a way that the data can be easily collected, validated, a very important issue I'll touch on in a little bit, manipulated, queried, reported, and shared with other systems. And I'm going to bring that home with this concept here. Create databases, not report bases. Now, you probably all have at least some aware of what database is. We created report bases. Don't feel silly that you don't know it. That's one of our terms. And we'll try to explain that. Generally, people do work with report bases, not databases. Here's a typical, here's a section out of a log. I pulled it run out of an example log. There are 2 columns here. This got a little big. And they wanted to show at some depth the moisture content, dry density, liquid and plastic limit, and the fines content. Very nice. Now, there are lots of ways of doing this. This is typically what's going to happen. Somewhere in the database, at depth 5, they put that exactly the way it's written. This is a report base. This is a dead end. You can't do anything more with it. Try parsing that. You have to depend on the user writing things exactly the same way. You'd have to write some very sophisticated parsing algorithms to be able to do things like plot PI against liquid limit. Or do other kinds of correlations. You want to show it as a plot, for example. You want to show a plot of moisture content versus depth. Well, good luck parsing it out of here. This is the way it should be done. It looks more complicated. There are now 3 tables involved instead of just 1. So at depth 5, we have a certain water content, wet density, and dry density. This is a liquid and plastic limit. This is a grain size distribution and has a certain percentage passing a 200 sieve. This is the way it should be stored. You should be storing your data with little or no regard how it will be used. That is not the job of the database. There should be no formatting here. This is just data collection. It's the job of the reporting tool to do this, to do plots, to do bar charts, to correlate, to do calculations, whatever. You want a repository and then let it do the work. Here's another case, which is not thought of so much. This is what typically people do when they write their descriptions. And we'll see in a little bit, this breaks first normal form of database design. You'll be well versed in that in a little bit. You've got a whole bunch of information in here. Again, try doing something with that except showing it on a log. You may want to query the database to ask, show me my layers with certain characteristics. Again, good luck trying to do anything with this. Number one, it's totally uncontrolled. People can type it any way they want. They could type medium dense as med dense or M dense or MD or whatever. This is a better way to go. This is what we call a component model. And each of these components have drop-down lists. People pick them. They can't just type what they want. So this is another approach. And then it can be formatted to any way you want. You can put them in any order, put a comma here, a colon there, put that in parentheses, make that uppercase. I want that one bold and that one red. And it could vary depending on the kind of reporting you need to do. And on your sections, you want to just see loose sand or a firm clay. Well, with this model, you can't do that. You'd have to create a whole new field with an abbreviated description. which is redundant data entry, one more opportunity to make a mistake. With this model, you just say, I want that field and that field. So, report-based database. So let's step back a moment and we'll cover some very quick database concepts. This is what database people do all day long. They have strange terminology. A table is a set of records. A table, think of a table in a database as containing related information. So you would have a table for project information, another one for borehole information, another one for sample information, et cetera, et cetera. And a record is just a set of related attributes. A record is where the data actually gets stored. So a table can have multiple records. A domain is a set of indivisible values as defined by the relational model. Indivisible means the values are atomic. It cannot be a set of values. The table below is an illustration of a table design that violates this definition. This does not match this description. You're putting multiple pieces of information in one field. That is a basic fundamental concept in proper database design, as were these here. You're putting lots of information in one field. You're putting lots of information in one field. That breaks this first rule. I'm going to skip over. By the way, I've sent out a paper that covers this better than just slides. And I've made that available to Professor Bardet. I want to talk mainly about normalization, how to normalize a database. And this covers some of the basic concepts. We're not going to spend a lot of time here. There are 3 rules, or what are called normal forms. There are actually 5, but nobody actually does 4 and 5 except academics. The first normal form states basically what we just said. You will not overload a field with multiple pieces of information. So the example here are the blows. There are 4 pieces of information here. So instead of doing this, you would do this. That's one case. Another common case that's not covered here, you'll see a field called water level or water depth in a database. And it's a text field. And the idea is people want to be able to type a depth to water or say not encountered. That's 2 pieces of information. And it allows uncontrolled data entry, which you want to avoid. So you really, in that case, you have 2 fields. You have one called water depth, and it's numeric. A water depth, by definition, is a number. And you only allow numbers. And you have another field that says water depth comment. Don't overload. That's this first rule. It's probably the most commonly broken one that I've seen. Second normal form states that a table that has a primary key with more than one attribute, the entire primary key must be related. I'll let you read about this in the paper. This is the formal definition. The example is better. So what we've got here, and we've seen this too, though not as commonly, they're putting all their depth-related information into one table. I've seen much worse than this. I've seen people put in lab results, field results, their descriptive information, color, water level, all into one table. And you want to put related information into a table. The sample information and the Atterberg limits really have nothing to do with each other. The value of the limits and even where you took the limits may or may not correspond to the blows. I've seen people put lithology information, layering information in a table like this. Well, Mother Nature doesn't care where you took your samples. The layering is the layering. They're unrelated to each other. They really should be in 2 separate tables. So we'd break it up. We have sampling information, and then we have laboratory information. This is a little trickier. What we've got here, this is pretty rare. I have seen people do this, but it is pretty rare. What they've done here, you've got a borehole information, and one of the attributes, at a certain date time, they took a water level. Well, if you now want a second water level, you have to add 2 more fields. Whenever stuff like that starts to happen, when you have more data of the same type and you have to change the database structure, bells should be going off. That's not right. These should be, again, in 2 separate tables. And so here we've taken it away from the normal borehole information. And now, to add more data, we just add another record. So those are the 3 basic rules of database design. Relationships are also very important in database design. And that's where relational databases come from. For example, in a database, you would not want to have a sample drilled from borehole B6 when borehole B6 doesn't exist in the database. That's called an orphan. And you don't want samples with no boreholes associated with them. There are exceptions. It can get a little tricky. But in our field, in geotechnical engineering, about 99.9% of the time, you want a borehole associated with all your subsurface data. So relational databases enforce those and the relationships can get very complex. And they do a number of things. Number one, they don't allow orphans. You cannot save with an orphan record. And if the parent changes its name, you can, the database will automatically cascade that update down to all the children. You don't have to worry about it. If you delete the parent, it will cascade that delete. It will delete all the children so that no orphans remain. You can have hierarchical databases, which is pretty typical of what we do, and you can have non-hierarchical databases. Won't be getting into that here. So this is a typical, very simple structure of our databases. A project has multiple borehole. A borehole will have multiple lithologies or strata, notes, groundwater samples, etc. These can have their own children that branch off, etc. More practically, this is what you can get. It can get a little complicated. Validation. Well, the first validation you want is what's called referential integrity. And that's where the relational model comes into play. If you end up with an orphan record, you've broken referential integrity. And most modern databases, all you have to do is set a few properties, and you can't break referential integrity. Appropriate data types. And this is another thing I see all the time. Many times clients will just make everything a text field, even though they're numeric, as I explained with water depth, so that they can put in notes. No, you really need to put it in a separate field. Calculated fields. Very typically, geotechnical engineers like to show recovery percent and RQD percent when you're in rock on your log. Nobody measures recovery percent, RQD percent. There is no such thing as an RQD percent meter or scale. You go out in the field and you're measuring a length of recovery, a length of all the pieces that are 4 inches or longer from the rock core to get RQD. And then somebody divides that by the sample run and multiplies by 100. But very typically, I look at our clients' databases, and they will have recovery and RQD as a percent in the database. Yeah, that works. But why? To me, you should set up a database to mimic the data you're collecting. Let the computer do the calculations. That's why God created computers. You record what you actually took in the field. And that does a lot of things for you. Number one, you have a record of what they actually measured. Number two, you avoid the possibility of somebody screwing up on the calculation. Now, there are reasons you would transfer the final result. For example, the AGS format in the UK requires that you do not transfer raw data, that you transfer only final results. And that's fine. That becomes a data view as far as I'm concerned. But the core information sitting in a data collectors or data generators database should be what they actually collected. Valid value lists, very important concept. And that is when you're on a field, you're given a list of values, and you got to pick one. This enforces consistency and avoids a lot of silly mistakes and gives you a hope, very good hope, of being able to query the data later. If you've got a field for log by, who logged the hole, and if it's an uncontrolled field, somebody types John Smith, somebody types J Smith, somebody else types JS, et cetera, et cetera, et cetera. Now, if you ever want to do a query, show me all the boreholes that were drilled by John Smith, forget it. The chance of you finding them all, you're going to have to try all the different permutations. If you have a valid value list and you all decide we're going to spell it J Smith, that's the way it's going to be. Everyone's going to use it. It's crucial for the ability to later query the data. And then various validation rules. You can set min and max values on various fields. And you generally, and there are some very simple ones you can put in, like min and max. And the valid value lists are a form of validation in themselves. However, there are lots of validation dependencies in our world. For example, very dense clay and stiff sand. They don't work. Sand is valid. Stiff is valid, but not together. Sample at 30 meters depth. 30 meters is a valid depth, but not when the hole is 20 meters. So you have these dependencies. Data by itself may be valid, but in conjunction with the other data, something's wrong. And then metadata, data describing data. We don't see enough of that, really. You should think in terms of, if someone were to open this database in 5 years, could they make use of the data? Is there enough information in there to describe how that data was generated? And you may not be giving it to your client, but something you want to store internally. And the client may ask for it as well. Usage transparency. We see a lot of funny naming of tables and fields. One of my favorite is water level. Is that a depth? Is that an elevation? And if it is a depth, what is it a depth below, etc. So naming, something as simple as naming fields and tables can really make a difference in the use of the database. And then data granularity, which we talked about earlier. Another way with data granularity, let me go back. This is another term for sort of report-based database. Boy, there's a lot of slides here. Okay. Yeah. This is coarse-grained. This is fine-grained. That's what I'm talking about with granularity. Okay, almost there. All right. Data interchange standards. We don't have many. I don't think we really have any data interchange standards in this country. It's a bit sad. A lot of data gets transferred. I'd say most data today gets transferred on paper. And it'll go up to the next level, a PDF or a CAD file. That's still paper, folks. That's not a database. It's just electronic paper. In the UK, they've had a interchange standard called the AGS. It's actually an industry group. It stands for the Association of Geotechnical and Geoenvironmental Specialists. And people have named the interchange standard after the industry group. That's been around since 1992. We were the first software product in the world to support it. And we still support it. I'm a contributing member to the committee. And they have a very different problem there than we do. In this country, when an investigation is done, generally the consultant will manage the lab and field work. They may not have their own rigs, they may not have their own lab, but they manage it. And they produce the final factual report, what we found, and they produce the recommendations for what to do on that job. In the UK, it's very different. There's a strong separation between the data generator, what they call the SI contractor, site investigation contractor, and the consultant, the data consumer. So what happens is the site investigation contractor goes out there, drills a bunch of holes. They have their own geologist and engineer logging the holes, their own laboratories, and they produce a factual report. Now, they have to get that over to the consultant, who then takes the factual report and does the engineering and makes a recommendation. And you can imagine on large jobs, you get plopped with hundreds of pages of factual report, and now you've got to dig through it all and analyze it. So they had enough of that in the early 90s, and they formed the committee, and they came up with this interchange standard. And it's still in use to this day. If you do work for most government agencies in the UK today, they require AGS, and for a lot of large consulting firms, and even on some of the smaller level. And that's very useful. In this country, we don't have that separation, so there isn't as much demand to make that work for us. That's too bad in a way. But more and more people are asking for data interchange, data to be provided electronically. And I think the real leading edge of that will be government agencies. It really has to be. Basically, it's going to have to get to the point where you give it to us digitally, you don't get paid. That's about the only way it's going to work. Because it's just more work as far as the consultant's concerned. But now we have reusable data. You look at some of the archive rooms at some of the State Departments of Transportation, and it's just many, many, many corridors full of paper. Just pretty much worthless. And it will be eventually. There'll be a flood someday, or just normal atmospheric conditions will rot it away. It's not a good site. I'm working on the DIGS committee, and it's a consortium of the AGS. We're working with the Brits on this one, and Cosmos and University of Florida. There are 16 State Departments of Transportation, the Army Corps signed on, the EPA, and the Federal Highway Administration. And the idea is to come up with one international standard for data interchange. We're in about our 4th year now, and it'll probably be a couple of more. So stay tuned. And one thing that's real important, data interchange design, an interchange format is not a database. There are things you do when you set up interchange standards that make life easier to interchange data. And they're horrible structures to work with from a database standpoint, and vice versa. Don't have time to go into that, but there really is a very strong distinction between a database structure, a well-designed database structure, and a well-designed data interchange structure. The idea is you can now work with whatever database structure is appropriate to what you need. And the client, or whoever you're sending it to, works with the database structure and the software they feel appropriate. And you can talk to each other through this interchange. Reporting. This is where you turn data into information. Otherwise, it's just a bunch of data lying around. And reporting can take many forms. An interchange standard, writing it to an interchange standard, your data, that's a reporting tool. You now have a different configuration of your data. A borehole log is a report. And running queries. Show me all my boreholes with certain layer characteristics, or show me all my boreholes, or show me the depth to the first SPT greater than 15 in all my boreholes. Send that to a file with the X, Y, and Z value of those numbers to a contouring program, and let's see what that surface looks like. The other thing you want to try to do, and this is where databases really shine, and the tools that go with them. Without databases, many times, or most of the time, you have people in the organization that know how to do things. And they know it really well. They've been doing it for 100 years, and they can take that data and manipulate it, and they produce these wonderful reports. And then they leave. And then somebody else has to rediscover it. With properly designed databases and the right tools, You can encapsulate processes. You now have a knowledge base. You are carrying information that someone has codified, and it's there forever. It can be modified, maintained, but that person leaves, that knowledge stays behind the database. For example, I mean, a very common thing, people do work with slope inclinometer or CPT. They want to get it into their database. They bring it up in Excel. They have to manipulate it in some way so that the database can read it. Then they read it in, and they do some other reporting steps. Basically, it's a very mechanical process. And if you're doing one a month, great, no problem. But if you're doing many a day, you don't want an engineer's time wasted on stuff like that. So there are tools available. You can actually encapsulate that process so that basically it's all written down. You hit a button, you pick the file, and it's all done. That's process encapsulation. Modeling. There are lots of great modeling tools out there. Some relatively inexpensive. You get things like Surfer. You can buy it for a few $100. You can do 2D modeling. Rockworks, somewhere around $3,000, and then you can get into some really high-end $50,000, $100,000 modeling packages. But they're all worthless without data, good quality data. And that's where another reporting tool pushing the data out to modeling software. Or in some cases, some modeling software can actually pull data from databases. But again, be careful. The map is not the terrain. You can be dazzled with some of these tools. They're really cool and produce some great stuff. But nothing replaces going out to the field and getting your hands dirty and digging, jumping into a test pit to verify what you think is really there. And now I'd like to show you a few. Whoops. Don't look. There we go. There, all right. Just to show you some reports very quickly. Slides, fit page. All right, here's a borehole log. This is a Canadian, Western Canadian form. There are regions that have their own feel to them for logs. I can generally tell you eastern to western Canada and southeastern US and California have some interesting things you don't see anywhere else. The Canadians tend to plot more than we do. We tend to have columns with numbers in it. They're both legitimate. Plots tend to take up a lot more room than just columns of numbers unless you overload them like what they do here. There are 4 different parameters being plotted in this one column. And next to it, of course, you've got your sampling, your stratigraphy, and the instruments you put in. So this way you can correlate data between them, and then you've got your metadata up top. Very typical format. And again, everything I'm going to show you can be done by hand without databases. But imagine trying to do all these things by hand as opposed to pulling it from one database. Just another example with a nested well. Now here we've got 2 very different pieces of information. You've drilled a hole, you've logged it, and then you went back later on and put a slope inclinometer in there. Sure, there's slope inclinometer software that will do these plots for you, but it would be nice to put them together with the actual drilling log. And even if you want, you could put in columns for various lab tests. Here's a rock log. Again, just superimposing different kinds of information. And now we're using bar charts and these funny dip angle plots instead of the normal plots we saw earlier for water content, because this data takes up a range vertically. So we'd use a bar chart instead of a plot. The Spanish love their pictures. This is, so you've got your rock cores right on your logs. So you don't have to be looking elsewhere. And an aerial view with the contouring, with the actual picture of the drill rig. You can do all kinds of fun things. Now this is CPT information. The data was imported. Again, this is an automated kind of process. The data was imported from various manufacturers. And unfortunately, every CPT manufacturer has a different file format. This is something we hope they will adopt DIGS so that we can write one import filter instead of dozens of import filters. And then calculations were made to correlate that CPT information to various equivalent soil behavior types using 2 different algorithms and correlating to, what do we got here, lateral earth pressure and friction angle. And there are lots of published information on that. This is an automated process. And now we start getting into sections, profiles, fence diagrams. They're called by many different names. Now we're looking at multiple boreholes with lots of different information. We've got the stratigraphy, we've got the well, we've got sampling intervals, and blow count versus depth alongside. And here's another example with a well, water levels, the site map showing the boreholes and the baseline that was used. And this legend here is automated. If there was no topsoil, this wouldn't show up. And here's another section showing CPT information alongside sampled boreholes. Here's an environmental. This is different than mine. Okay, let's go this way. Environmental data. These are various analytes. And every place a test was run, a little square is made. Either green, it passed, red, it failed. And so you can quickly see at a glance where your problems are. And it shows the site map and plan. Again, all this can be done by hand. Here we have another section. These lines were not done by hand. They were the surface elevations and the north and east coordinates were sent out to a contouring program, in this case Surfer, and then the whole surface grid was brought back into the program, and this the same with bedrock. And then we drew this section and we cut out a profile line from that surface and superimposed it. It's about as close as we get to interpretation. We try to avoid interpretation, but so again, superimposing different kinds of information. And here's a 3D view with the site map to give you some sense of where you are. And something as simple as, water level with time. People generally don't put this in a database. They just throw it in an Excel spreadsheet somewhere. Oops. And this is pore water pressure dissipation with time from the CPT rig. And then your standard lab kinds of things, the Atterberg limit plots. Again, this one piece of information, liquid limit, could show up here. We've also seen it on a log. You can put it on a fence. It can be put in lots and lots of different uses. Ternary diagrams, the Illinois DOT uses this, USDA uses a ternary diagram. It's a textual classification. They don't care about plasticity. They only care about grain size. The agronomists use this mainly. Stereo nets. Tabular results. Very, very simple thing to do and no extra work if you're working from a database. You set up the form once and you can get a dump of your whatever data you want very, very quickly. Well development records, just various ways of presenting tables. Histograms, frequency distributions. We as geotechnical engineers, at least in this country, don't do enough statistics. We really don't. They're very heavy on it in the UK. It's very useful when you're talking about environmental studies with various chemical constituents. But even for a geotechnical study, one thing I've taught a number of our clients to do is in site characterization. You go through, you've got 1,000 boreholes, and you know there are some consistent layers through your site. And you go through, you look at the logs, you look at sections, and you start going through and start making decisions, engineering decisions. And you say, I'm calling this layer A from this depth to this depth in this borehole. And this is layer B and layer C. And you go through all your boreholes and you do that. I have done this process back in my youth, but by hand. And then you start asking for, let's say it's a foundation study. What's important to you in a foundation study are strength, mainly, and compressibility. So you start saying, for layer A, show me some strength parameters, some frequency distribution. And if you get a double hump, excuse me, if you run a histogram and your data looks like this, what that generally means, well, it definitely means you have two populations. One of your layers really has a sublayer. And then you go back and you clean that up. And you keep doing that until you've got a good site characterization. Then you can start doing things like, show me my average properties and start identifying these layers throughout the site. So even histograms have uses. This is an incremental histogram for various chemical constituents. Here's another view of data which is not used enough, I don't think, in our field, and that is a plan view. And again, this is environmental data. It could be just as easily for geotechnical kind of information. So what we've got here is one analyte, arsenic, and a red borehole indicates that at least one test failed for arsenic in that hole. Green means all the tests were run past. Gray means we didn't run that test anywhere in that hole. So at a glance, you can tell quite a bit with these kinds of views. This one's the same thing, but we're showing 4 different analytes. We're quartering the data markers and using the same kind of legend. This was done by our rep in the UK. Similar thing, I forgot why I wanted to include this one. How's it different? And then tabular summaries, and they've done some interesting things here. Things that are in red, fail, and underline, and italics means something else. I've forgotten. And then we start looking at modeling. So this was taken from a database. We extracted the x and y coordinates and some z value, whether it's top of water, top of ground, top of bedrock, bottom of aquifer, whatever you want. But that's all in the database. Once you've created a subsurface database, you have a tremendous amount of XYZ information. Make use of it. And now we're looking at a solid model. So again, every piece here was taken from the database. What did it was not a database program. This happens to be RockWorks. It's a modeling program. There are lots of modeling programs out there. We extracted the borehole information. Those lines are boreholes with borehole names up top with their proper locations. And this particular, what we're plotting here is PID values. It could be blow counts. It could be C values, phi, whatever. And we've told the model to only show us up to, let me see, ignore the lower values. Only show us the higher values starting at a certain value. So now we're looking at hotspots of PID at a certain concentration. These are 3D contours. And it's telling you the volume. Some very, very nice tools. And you can do 3-dimensional stratigraphic kinds of models. And again, this is taken from point information, boreholes at various locations. They have an algorithm. Do you believe it? This is just a tool. Don't rely on it totally. It can be a reality check for you. It can open up ideas on what's going on. They also have the ability of cutting a slice through here so you can look at it in section. Google Earth. That's another way to publish your data. And you can do a lot of neat things with Google Earth. It's not actually Google Earth that you work with. You work with an interchange format called KLM, KML. Thank you. Keyhole markup system, language, sorry. It was purchased by Google a few years ago. And it's a way of transferring spatial information. And I believe Civil 3D, AutoCAD Civil 3D, and ArcGIS now support it, as well as Google Earth. And you can put in some really neat things, like you can put links in to photographs. And these photographs could live on a server halfway around the world, or it could live on that system. You can put in information that will pop up attributes, whatever information you want. You can put in links that will pop up a PDF. So it's just another way of publishing your data. And it's pretty impressive. You send a little KML file to your client at the end of a job, and all the graphics are sitting on a public zone on your server, and they can see all this stuff. ArcGIS, or GIS in general. And we're seeing more and more of this, where you're linking subsurface information to a GIS model. And we're doing a lot of customization for some of our clients. And a lot of our clients have done a lot on their own. There's a public website for the Minnesota Department of Transportation. They've got about 30,000 boreholes. And right now they're just PDFs. Throughout the state, you can zoom in, click, and a PDF comes up with a borehole. And this is, again, Google Earth. Unfortunately, Google Earth, you can't rotate to look underneath. So we had to put the boreholes on top. And you probably can't see it too well, but they are colored in strips indicating different materials. And the other thing, which, I don't know, what is going on here? Just a moment, I'll get there. There we go, it was off screen. This is a 3D PDF. Adobe made this available, I think, starting last year. And a number of programs support this now. We're working with it, something we've generated. The next step is to put a grid surface over top and then drape an aerial photograph over it. And then we're also looking at the ability of showing different kinds of information. For example, if you're doing an environmental study and you're interested in permeability, you've done a lot of permeability tests, you might have a disk that grows bigger or smaller depending on the permeability at wherever your tests are. Or it could be strength parameters, consolidation parameters, whatever. So we're really excited about this. Basically, once you've generated this, anybody that has Adobe Acrobat Reader 8 or 9 can view it. And you can do fun things with it. We're just starting to play with this, and it's been a lot of fun. Okay, so to summarize, basically, get your data in one place, in a place that is well designed and where the data can be reused easily, it's properly validated, and then hook it up to whatever you need to hook it up to get you the data views you need. Well, thank you very much for your time. I appreciate it. Are there any questions? Thank you.
Question from the audience?
That 3D model, was it Rockworks?
Which one? This one here or the earlier? No, that was Rockworks. Yeah. Yeah. And again, though, we didn't build that manually. We took data right from a database, dumped it into a format they could read, and then turned it away. Yes?
All the applications you showed, they're using relational database?
Yes.
How do you choose relational database?
Well, just about everything is today. Though, for example, Access. Access is a workhorse. It does the job. It's not an enterprise system. You wouldn't try to store every project you've ever done for the last 10 years on it. But it's a great place to start, and our program is based on Access and SQL Server, which is more of an enterprise backend. You can still take a database that's capable of really good design and relations and all that stuff, and not do any of that. And so you end up with just an Access file or a SQL Server file with no intelligence, no relations whatever. You have to basically build in the relations. You have to say that this is related to this and how it's related.
So do you think it's the future? You still, I mean, in the future, DIGS is still planning to use relational database, or they're...
Well, again, DIGS is just an interchange standard. It's not a database. It is just, yeah. But people have been using relational databases in our field for 20, 30 years. They're out there. Just don't try to use Excel as a database. No, I can't. I can't. They're our biggest competitor, so I'm always bad-mouthing them. You know.
Do we have anybody online? Okay, so if they want questions, raise your hands using your little tool, and then we'll be able to, or can you unmute them?
Yeah, I will do that.
Okay. Do we have any questions from our, those listening online?
They're just,
I think I'm going to take that as a no. All right.
they're stunned.
All right. Any more questions from the audience? Okay. In that case, we should thank our speaker. Thank you.
Thank you very much. All right.
Okay. Cynthia, you can cut.
Very nice meeting you.
Oh, forse salida.